Hello. We will wait for a couple of more minutes. If anyone else doesn't join, then we can start by 7:05. Okay, so let's start. Good evening, everyone. I am Rahul Patel from Department of Chemical Engineering, IIT Bombay, and we are conducting this weekly 1 hour sessions to solve previous year GATE questions. So let's start with the first one today. So the first one is question number 7 from GATE 2018 from GATE 2018 from Chemical Engineering, and the subject is heat transfer. And the question is the economy of evaporators used for concentrating sugarcane juice is dash. So basically we have to define that how economy of evaporator is calculated. So does anyone amongst you to know the correct answer? How do we define economy of the steam evaporator? You can write in chat box or speak up. Okay, so let's go with the basics. So an evaporator is a heat exchange device which is used to concentrate the solution. When I say concentrate the solution, it means that to evaporate the solvent from the solution. So that will be basically concentrating my solution. And we usually do this by providing steam to the evaporator. So yes, so there is this general definition related to the steam evaporator terms. The first one is capacity, where capacity is defined as number of kgs of water vaporized per hour. And then the second definition is economy, and economy is the number of kg of water vaporized per kg of steam fed. And in the given question, we were asked to find the economy of evaporators. So from this statement, we can write that steam economy is defined as kg of water vaporized upon kg of steam fed. So yes, if we look into these given options, the first one is kg of concentrated juice produced. So this one isn't correct option. The second option is kg of steam supplied upon kg of sugarcane juice fed. So again, this is also incorrect. The third option is kg of water vaporized upon kg of steam supplied. So this option matches with our definition, and this is the correct option. And the last one is kg of sugarcane juice fed upon kg of water vaporized. So this is also not the definition of steam economy. So that is also a wrong option. So from the given 4 options, the correct answer is option C, that is kg of water vaporized upon kg of steam supplied. So we can select this option C amongst the given 4. Now let's look at the second question. This is question number 8 from GATE 2018 Chemical Engineering paper. And the question is segmental baffles in 2,4 shell and tube heat exchanger, and we have been given 4 options. So basically we have to find the function of baffles in the cell and tube heat exchanger. That is, why do we introduce or keep baffles in the cell and tube heat exchanger? And the first option is change the flow pattern of tube side fluid and increase the overall heat transfer coefficient. Second option is increase the heat transfer coefficient in the cell side and support the tubes. Third option is help to reduce the thermal expansion of the tubes and increase the heat transfer coefficient in the tube side. And the last option is increase the number of passes in the cell side and increase the heat transfer coefficient in the tube side. So we have to choose the correct option, correct reasoning for why do we keep the segmental baffles in cell and tube exchanger. If you have any idea about this answer, you can write it in chat box. I'll just wait a couple minutes. You can write the correct option in the chat box. This is a fairly simple question. Okay, so let's just look at the general schematic of this shell and tube heat exchanger. So this is a single pass and single tube kind of shell and heat exchanger. As the tubes, this is the tube side fluid and it will only pass one side along the length of the heat exchanger. That is why we call it a single pass. Similarly, the shell side fluid will enter over and only travel once along the length of heat exchanger, and that is again why we call it as one pass, one shell pass. Similarly, if we want to look into this 2-4 shell pass, so basically it will be 2 times of shell pass and 4 times it will pass through the tubes. So now looking at the given options, so the first one is change the flow pattern of the tube side fluid and increase the overall heat transfer coefficient. So from the given diagram, we can see that for the tube side fluid will flow through the tube and it won't be hindered by the baffles. So the flow of this tube side fluid won't be disturbed or won't change or won't be affected by these baffles, and hence the flow pattern of the tube side will remain the same. That is why we have marked the option as incorrect. And the second option is increase the heat transfer coefficient in cell side and support the tubes. So yes, the secondary purpose of the baffles is to support the tubes. So these are the baffles, and here we can see that they do serve the purpose of supporting the tubes. And also by introducing these baffles when a fluid is entering the shell side, we are basically introducing the turbulence in the shell side. And due to the increase in turbulence, the heat transfer coefficient of the shell side will also increase. So this option B is correct one. And similarly, in option C, we have been given that it helps in reducing the thermal expansion of tubes. So that is also incorrect option. And in option D, we have been given that it increases the number of passes in cell side and increase the heat transfer coefficient in tube side. So is this tube side flow won't be affected and the heat transfer coefficient will remain the same no matter whether we introduce or whether we have baffles or not. So the last option is also incorrect. So from the given options, we have this option B as the correct one. Yes, so the purpose of introducing the baffles in any shell and tube heat exchanger is to increase the turbulence of the shell side fluid, which will thereby increase the heat transfer coefficient. And the other purpose of the baffles is to support the tubes. So yes, from the given option, we have selected this option B as the correct one. If you have any doubts in the previous two questions, you can just ask in the chat box, or else we will move on to the third question. So the third question is from GATE 2018, question number 34 from heat transfer. And here we have been given an insulated storage tank which contains 1000 kg of liquid of specific heat, the given value. The liquid is heated by saturated steam condensing in a helical coil at temperature of 180 degrees Celsius. The heat transfer area of the coil is 0.1 meter square. The overall heat transfer coefficient is constant at the given value, then the time in hours required to raise the temperature of the liquid from 20 to 80 degrees Celsius is dash. So here we have been given an unsteady state problem in which we have been given an insulated storage tank with a liquid, and we have to find the time taken to raise the temperature of that fluid from 20 to 80 degrees Celsius. So let's look at the video solution prepared for this question number 34. Hello everyone, this is question 34 of GATE 2018 chemical engineering paper from the subject of heat transfer, and the question is, an insulated storage tank contains 1000 kg liquid of specific heat 10 kilojoule per kg Kelvin. The liquid is heated by saturated steam condensing in a helical coil at a temperature of 180 degrees Celsius. The heat transfer area of the coil is 0.1 meter square. If the overall heat transfer coefficient is constant at 1000 watt per meter square Kelvin, then the time in hours required to raise the temperature of the liquid in the tank from 20 to 40 degrees Celsius is dash. So for the given setup of this insulated storage tank, we have been asked to find the time in hours required to raise the temperature of liquid in the tank from 20 to 40 degrees Celsius. So let's just consider a tank. So from the given question, we have an insulated tank. And it has some liquid with a specific, and the mass of the liquid is 1000 kg. The specific heat Cp is given as 10 kilojoule per kg Kelvin. Let's just change this into joule per kg Kelvin. So it will be 10 into 10 raised to 3 joule per kg Kelvin. The liquid is heated by a saturated stream in the condensing helical coil. Okay, so let's just consider a helicoil coil inside the tank, and the temperature is 180 degrees Celsius for the helical coil. So just the temperature of coil is 180 degrees Celsius, and the area of heat transfer is 0.1 meter square from here. The overall heat transfer coefficient is kept constant. U is 1000 watt per meter square Kelvin. Then the time required to raise the temperature of liquid in the tank. Okay, so my T initial is 20 degrees Celsius and T final is 80 degrees Celsius. So from the given setup, we can write the energy balance. So usually the energy balance is written as mCp delta T is equal to m dot Cp delta T is equal to UA delta T. So that we can rewrite it as the mass present in this system into Cp into dt upon T. Here the temperature will be changing with time because we have been given an unsteady state system, and this will be equal to the temperature what the heat gained or lost by the fluid. So that is given as UA delta T. So we will just replace the values over here. So mass we have been given 1000 into Cp is 10 raised to 4 from over here. Then dt upon dt we have to find overall heat transfer coefficient U is given as 1000, area is 0.1 meter square into delta T. So yes, in this case the delta T is the heat exchange between the fluid and the helical coil. So that is delta T is the for the coil the temperature we have defined as T coil minus T is my temperature of the fluid. So the temperature of coil we have been given as 180 degrees Celsius and minus T. So this is my delta T. So this we can write it as thousands will get cancelled and this will become 10 raised to 5 dt upon T is equal to 180 minus of T. Correct? So this we can also write it as 10 raised to 5 180 minus T dt is equal to dt. Now we will be integrating this equation to find the temperature variation along with time. So, so initially the temperature was 20 and finally it becomes 80. So 20 we have considering time as 0 and we have to find this time at which the temperature becomes 80 degrees Celsius. We can integrate this as minus of ln of unity minus t. It will go from 80 to 20, and we will do 1 over 10 raised to 5 into t minus of 0. So yes, now we can replace the corresponding values, and it will become so you can replace all these values and you will be getting this term as 0.47. So time will become 0.47 into 10 raised to 5. This will be in seconds, and you need to divide it by 3600 since we have been asked to find the final answer in hours. This will become 47,000, and the final answer will come somewhere around 13.05 hours. Yes, in this given question, we wrote the unsteady state mass balance, that is MCP delta T equal to UA delta T, and find the time required to raise the temperature by the given delta T. And the final answer is 13.05, and we have to write it in second decimal places. So we will report the answer as 13.05. So if you have any doubt in this question, you can write it in chat box. I'll wait for a minute. So just to revise, in this given question, we had written the energy balances mCp dt upon dt is equal to UA delta T. Basically, then we integrate this equation, that is UA upon mCp from delta T into dt. Then we integrate this equation to find the temperature as a function of time. So at any given time, we can find the temperature of the fluid inside the vessel. The similar concept we use for lumped heat capacity analysis also. Yes, now let's look at another question. This is question 35 from GATE 2018 chemical engineering paper from the heat transfer subject. And here we have been given the wall of a pipe of radius 1 meter is at uniform temperature of 200 degrees Celsius and is covered by insulation of thickness 0.1 meter. The ambient air outside the insulated pipe is 20 degrees Celsius and has heat transfer coefficient of 10 watt per meter square Kelvin. The thermal conductivity of the insulation material is 0.05 watt per meter per Kelvin. If the heat transfer occurs at steady state, the temperature of the outer surface of insulation is there. So in the earlier question, we were given an unsteady state problem, and in this question, we have been given a steady state problem, whereby we have been given a pipe which has been insulated with a material, and we have to find the temperature at the outer surface of insulation. So let's look at the video solution. Hello everyone, this is question number 35 of GATE Chemical Engineering 2018 paper from heat transfer. The question is, The wall of a pipe of radius 1 meter is at uniform temperature of 200 degrees Celsius and is covered by insulation of thickness 0.1 meter. The ambient air outside the insulated pipe is at 20 degrees Celsius and has heat transfer coefficient of 10 watt per meter square Kelvin. The thermal conductivity of the insulation material is 0.05 watt per meter Kelvin. If the heat transfer occurs at steady state, the temperature in degrees Celsius of the outer surface of insulation is this. So for the given system of cylinder and insulation, we have to find the temperature at the outer surface of insulation. So for the general schematic will look somewhat like this. So here we are having pipe, and the internal temperature we have been given Ti. So that is Ti we have been given as 200 degrees Celsius, and radius R is 1 meter. And then we are having an insulation. The thickness of insulation we have been given as 0.1 meter. And the ambient air outside is 20 degrees Celsius. So that is T infinity is 20 degrees Celsius. And the heat transfer coefficient is 10 watt per meter square Kelvin. The thermal conductivity of the insulation material is 0.05 watt per meter Kelvin. And the heat transfer occurs at the steady state, the temperature at the outer surface of the insulation. So we have been asked to find temperature over here. So let's just consider it as Ts. Now considering this system, we can write the resistance as, so initially the temperature was Ti, then we are having this conduction resistance due to insulation. Let's just call the resistance due to conduction as R1, and then over here the temperature is Ts. Then again we will be having convection resistance. So let's just call it as R2, and finally we'll be having this T infinity. So this is 200 degrees Celsius. This we have to find, and T infinity we have been given as 200 degrees Celsius. Now for the cylindrical system, the resistance we know as ln of R0 upon Ri upon 2 pi KL. Similarly, for convection, we know that the resistance is written as 1 upon H0 upon area. The E0 where E0 is the external area, so basically the area of this surface. So we can find both of these R1 and R2. So let's just calculate this. It will become ln of, so the outer radius will be 1 plus thickness of the insulation, that is 1.1 upon 1 upon 2 pi KL. So you can replace the value of K as 0.05. So this will become 20 into ln of 1.1 upon 2 pi L. And we can solve this, and the answer will be 1.9065 on 2 pi L. Similarly, we can find the R2, that is the resistance due to convection, as 1 upon H naught E naught. Here H naught we have been given as 10 into 2 pi. The external radius is 1.1 into L. This will become 1 upon 11 into 2 pi L. This, now we are having R1 and R2. So for the given resistance diagram, Ti, Ts and T infinity. So if we write the energy balance, we can write this as, the overall heat flux will be Ti minus T infinity on, so this is Ti and this is T infinity, and between them we are having two resistance. It will become R1 plus R2. So this will be equal to Ti minus Ts upon only one resistance between them, that is R1. Similarly, this will become Ts minus T infinity upon R2. So you can use any of the two terms and ultimately find the temperature of the surface. So let's just consider these two terms for our purpose. So Ti we were given as the inside temperature is 200 degrees Celsius minus Ts we have to find, and R1 is this term, that is 1.9065 into 2 pi L. So this is Ts minus T infinity. The ambient air temperature was 20 degrees Celsius, and R2 is 1 upon 11. Okay, 1 into 11 into 2 pi L. So 2 pi L will get cancelled out. Here we can write this as 200 minus Ts is equal to 11 into 1.9065 into Ts minus 20. So this will become 11 into 1.9 will be somewhere around 20.97. So this will become 20.97 into 2s minus of 419. This will become 20.97 plus Ts, 21.97 Ts is equal to 619. So from this we can get Ts as 619 upon 21.97, and this will become 28.174 degrees Celsius. So the final answer, that is the temperature at the outer surface of insulation, is 28.17 degrees Celsius. So we can write the final answer rounded off till second decimal places as 28.17. We looked upon the solution of this question, in which we had to write the heat balance and consider the resistance, convective and conductive resistance. And ultimately we find out the temperature at the outer surface of the insulation. So this is the formula of resistance, formula for conductive resistance for cylindrical system. So you can remember this formula, and for this convection it is straight away easy to calculate. And then we just draw a temperature resistance diagram and then equated this equation to find the outer surface of temperature, to find the temperature at the outer surface of the insulation. If you have any doubts, you can speak up or write it in the chat box. We will move on to the next question later. Am I not audible? I think I should be audible now. Okay, so now let's look at question number 36. And in this question we have been given vapor bubbles are formed in the nucleate boiling region at frequency of 10 bubbles per second per nucleation site. There are 100 nucleation sites per meter square of heating area. The latent heat of vaporization and density of vaporization and density of vapor under the operating conditions are 1000 kilojoule per kg and 1 kg per meter cube respectively. The diameter of bubble is 10 raised to minus 3 meter. Assume that the entire heat supplied is used for vapor generation. the heat flux is dash. So this question is related to the boiling and evaporation topic, and we have been given this nucleate boiling regime and asked to find the heat flux. So there won't be much formulas in this question. We have to just use the given data and just match the units to find the heat flux. So let's see how we do that. Hello everyone. We are solving question 36 of GATE 2018 chemical engineering paper from the subject of heat transfer. The question is vapor balance. Vapor bubbles are formed in nucleate boiling regime at frequency of 10 bubbles per second per nucleation site. There are 100 nucleation sites per meter square of heating area. The latent heat of vaporization and density of vapor under operating conditions are given as 1000 kJ per kg and 1 kg per meter cube respectively. The diameter of each bubble is 10 raised to minus 3 meter. Assume that the entire heat supplied is used for vapor generation. The heat flux in watt per meter square of heating area is dash. So for this given boiling scenario in this nucleate boiling regime, we have been asked to find the heat flux in watt per meter square of heating area. So yes, so let's just consider this is a vessel, and from here we are providing the heat. We are having the fluid inside the vessel, and in this nucleate boiling regime, so bubbles will start forming at the surface. So let's just consider these are my bubbles, and these bubbles will help to exchange the heat. So now from the given question, we will write the data. So vapor bubbles are formed at the frequency of 10 bubbles per second. So let's just call this frequency as small n is equal to 10 bubbles per second per nucleation site, and then there are 100 nucleation sites per meter square. Let's just call this as capital, and this we are given as 100 nucleation sites per meter square of heating area. The latent heat of vaporization, so that is, let's just call it as Q vaporization, as 1000 kilojoule per kg, and then density of vapor, raw vapor, we have been given as 1 kg per meter cube. The diameter of the bubble is 10 raised to minus 3 meter. Assuming that the entire heat supplied is used for vapor generation, the heat flux is given as. So here we have been given that the entire heat supplied is used for vapor generation, and we have been asked to find the heat flux. So basically the heat flux, you can write this as heat flux is equal to, see, here we are providing heat and then the bubbles are formed over here. So basically these bubbles will be having this latent heat of vaporization. So and that will be used to for the further boiling of the liquid. So that and total heat flux we can write it as the number of bubbles into the heat provided by each of these bubbles. So that is heat supplied by, let's say, one bubble. So we have, and this we have been given as, this is Q vaporization. So ultimately we have to find the number of bubbles and then multiply it by Q vaporization, and we can get the total total heat flux. So to find the number of bubbles, let's just find the total volume of the bubbles. The volume is defined as 4 by 3 pi r cube. This we can write it as pi by 6 d cube. The diameter of bubble we have been given as 10 raised to minus 3 meter. So the volume of the bubble is pi by 6 into 10 raised to minus 3 meter cube. Similarly, the mass of the bubble we can find it as mass is equal to rho into V. The density we have been given as 1 kg per meter cube. Ultimately, the mass will become same as volume 10 raised to minus 9. Minus 9 kg. Now here we have been given Q vaporization per kg of bubbles. So let's just write it over here. Q vaporization we were given as 1000 kilojoule per kg of bubbles. So ultimately we can find this Q vaporization as heat supplied to form so we will multiply this by the total mass of the vapors. So that is 1000 into the mass of the vapors we have found it over here. This will become pi by 6 into 10 raised to minus 6. So yes, this 1000 was in kilojoule per kg. So this will become, let's just change this kilojoule into joule to become joule. This is for each bubbles. Q of bubbles will become pi by 6 into 10 raised to minus of 3 joule. So now to ultimately find this heat flux, we have to multiply this pi by 6 into 10 raised to minus 3 into number of bubbles. So the number of from this, so we are having 10 bubbles per nucleation site. 10 bubbles for one nucleation site, and we are having total 100 nucleation sites. 100 nucleation sites. So for these 100 nucleation sites, we will be having 100 into 10, that is total 1000 bubbles. Please, we can multiply this by over here. That will become pi by 6 into 10 raised to minus 3 into total number of bubbles, that is 1000. So ultimately the heat flux will become pi by 6. So this will come around 0.5235 watt per meter square. So the final answer is the heat flux will be 0.5235 watt per meter square. So that we can round off till third decimal places as 0.524. So the final answer, that is the heat flux, is 0.524. So in this question, we looked upon how to calculate the heat flux by using the latent heat of vaporization and multiplying it by the total number of bubbles formed. So first we found out how much heat is provided by each of these bubbles, and then we multiplied it by the total number of bubbles. The total number of bubbles were just simply calculated by using the first two information. So that is, we were provided 10 bubbles per second per nucleation site, and we were given 100 nucleation sites per meter square. And that implied that there were total 1000 bubbles per meter square of heating area. Then from this information, we were given the latent heat of vaporization in kilojoule per kg. So from this, we found out for one bubble how much amount of latent heat of vaporization was found. So basically, we had to convert this we had to convert this 1000 kilojoule per kg into 1000 kilojoules. So we found out the mass of the bubbles using mass is equal to rho into V, and then multiplied it by this 1000. And that gave us the heat of vaporization for each bubble, and then we multiplied it by total number of bubbles to find out the entire heat flux. Also here we are having a typo. This should be 10 raised to minus 9 over here. Okay. So if you have any doubt in this question, then you can write it in chat box. Okay. So I'll just quickly explain the question again. So see, in this question we have been asked the entire the heat flux. The total heat flux we have to find, and there were some bubbles. These bubbles are formed as we are operating in the nucleation regime, or else there would be some other forms of bubbles. But since we are in nucleation regime and the bubble formation just started, we consider them as spherical. So the total heat flux will be what? The heat from one bubble into total number of bubbles. Okay. So let's say if the heat from one bubble is Q1 and there are total n bubbles, so the heat will be Q1 into n. Now we have to find both of these terms, n and Q1. So to find this n, we will use the first two line of information. So over here we have been given that vapor bubbles are formed at the frequency of 10 bubbles per second per nucleation site. Okay, and there are 100 nucleation sites per meter square, so we can just multiply it by 100. So 100 nucleation site per meter square. So that will basically give us 1000 bubbles are formed per second per meter square. So this, we have this n. Now we have to find heat from one bubble. So for this we have been given the latent heat of vaporization as 1000 kilojoule per kg. So that is 1000 kilojoule per kg. Now we have to change this to kilojoule per bubble. So that is, we can multiply this 1000 into mass of each bubbles, and this mass we calculate it as rho v. So mass into rho v, and the volume was pi by 60 cube, and density we have been provided. So from here we will be getting the heat supplied by each of the bubble, so that we will be basically putting over here and multiply it by total number of n. So that is how we solved this question to calculate the heat flux. So you can just quickly take a look upon here. So here we had calculated the volume. This is the mass by using the given volume. Now once we have this mass, we multiplied it by this 1000 kilojoule per kg to change it into joule per bubble. And then we calculated the total number of bubbles and then multiplied both the terms to find the heat flux in watt per meter square. I guess that would have explained, and we can now move on to the next question. So the last question for today's session is question number 55 from grade 20 in chemical engineering paper, and this is related to shell and tube heat exchanger, in which we have to compare the counter current and co-current option. So basically, any heat exchanger can operate in counter current fashion or co-current fashion, and how much difference will that make in the heat transfer area? We have been asked to calculate in the given question. So let's look at the video solution. Hello everyone. We are solving question 55 of grade 28 in chemical engineering paper, and the subject is heat transfer. The question is, a hot liquid is to be cooled in a 1-1 cell and tube heat exchanger from 80 to 50 degrees Celsius. Cooling water enters the tube side at 30 degrees Celsius and exits at 45 degrees Celsius. The properties of liquids are constant. Also, the overall heat transfer coefficient is same for counter current and co-current modes. The percentage saving in heat transfer area for counter current option with respect to the area of co-current option is dash. So for the given shell and tube heat exchanger, we have been asked to compare the performance of this counter current as well as co-current mode. So for a general schematic of any shell and tube heat exchanger will be like this. Let's say we are having multiple tubes. So from here my shell side fluid will enter, and it will get, so T in minus T out, and from here my tube side flow will enter and it will get out. So now if in this the direction of both the cell side fluid and tube side fluid is this, so this is my co-current flow, and if I introduce this shell side from over here and bring it out from over here, then the flow direction will be opposite, and that will become my counter current flow. So for both of these cases, we can draw the temperature profile as, let's just write this co-current flows. So along the length of the heat exchanger, so the hot liquid, the temperature of the hot fluid will decrease from 80 to 50 degrees Celsius, and the cooling water enters the tube side. So for tube side, it will increase from 30 till 45 degrees Celsius. The flow directions are same. Similarly, for counter current, we can draw the profile as, the direction of will be opposite. So the temperature of the hot fluid will decrease from 80 degrees Celsius to 50 degrees Celsius. The temperature of the cold fluid will increase from 30 degrees Celsius to 45 degrees Celsius. And direction will be opposite to the first one. So for both of this fluid, the heat exchange, the usually from the energy balance we can write that Q is given as UA delta T LMTD, and this will become QH, that is heat exchange by the cold fluid, or the QC, where QH is, you can write it as MCP of hot fluid into delta T. For cold fluid, you can similarly write it as MCP of cold fluid into delta T. So ultimately, we have to calculate this log mean temperature difference and then equate all this equation. And log mean temperature difference is defined as delta T1 minus delta T2 upon ln of delta T1 upon delta T2. So the log mean temperature difference for co-current flow, we will find it as delta T CO is, here delta T1 is 80 minus 30 is 50. It is delta T1 is equal to 50 and delta T2 will become 5. So we can write this log mean temperature difference for co-current flow as 50 minus 5 on ln of 50 by 5. This we can write it as 45 upon ln of 10 302, and this will become 19.54 degrees Celsius. Similarly, for counter current flow, we can write it as, here your delta T is 20 degrees Celsius, and on this side delta T2 will become 35 degrees Celsius. So we can write this as 20 minus 35 on ln of 20 upon 35. So this will become minus 15 minus of 0.5596. This will come around 26.804 degrees Celsius. So for both of this co-current and counter current flow, we are having log mean temperature difference. And now we can write this as, we know that U UA delta T LMTD for, let's say, co-current flow will be equal to mass flow rate of cold fluid, Cp of cold fluid, into the temperature difference of the cold fluid. So here delta T for the cold fluid will be 45 minus 30. Similarly, for the hot fluid, we can write this as delta TH, delta TC. Here delta TH will be 80 minus 50. Now similarly, for the co-current flow, for the counter current flow, we can write it as UA LMTD upon CC is equal to, now the heat exchange will remain same as the counter current flow because the mass flow rate is same, Cp will remain same, and delta Tc, that is the temperature difference of the cold fluid, will be same as the previous one. So ultimately this term is equal to this term and this hot term will be equal to this term, and we can take the ratio of this equation and we can write it as UA delta TLMTD co-current flow upon UA delta T upon counter current flow. So ultimately these two terms will remain same, that this will become 1. And from the question we have been given the overall heat transfer coefficient is same for counter current and co-current mode. So this U will also get cancelled. And let's just call the area for the counter current flow as ACO, and for area for co-current flow as ACO, and area for counter current flow as ACC. So this will be equal to delta T LMTD for counter current flow, and this will become LMTD for co-current flow. Okay. So this we can write it as delta T for counter current flow was given as 26.804 upon for co-current flow it was 19.54. So we can calculate this and it will become 1.37. So ultimately we are having area for co-current flow upon area of counter current flow as 1.37. Now we have been asked to find the percentage saving in heat transfer area for counter current option with respect to the area of co-current option. So that is, we have been asked to find ACO minus ACC upon ACO. This will be equal to 1 minus of ACC upon ACO. This we can calculate it as this will come around 0.271. So ultimately in percentage, the savings can be written as 27.1%. So yes, so if the mode of the flow is counter current, then we will observe 27.1% saving with respect to that of co-current flow. That is why we can go ahead with counter current option as it really what we will be saving on the heat transfer area. Yes, the final answer we will report it as 27.1. Okay, so do you have any doubts in any of the questions that we discussed today? This was the last question in which we compared the counter current and co-current flow kind of heat exchanger. If you have any doubts, you can ask, or else we can end today's call. I'll be here just for a couple of minutes more. If any amongst you two have doubts, then okay, you can ask. Okay, so if you don't have any doubts, Gopinath, then we can end today's meeting. Thank you for joining. Okay, bye everyone.